I think calculating conditional probabilities with the table approach is a great way to go about doing it because it helps to build in a connection about what the probability is asking and the real world by considering a large group of individuals or a large number of trials and just seeing what happens. Now, once you're comfortable with the table method, and if you really like mathematics, you might enjoy actually solving some of these problems with just the mathematical way, using a formula called Bayes' theorem, which is, in my opinion, I think one of the most important, maybe top 10 formulas in probability that's ever been discovered. So for this section, I'd like to go over some of the math behind these conditional probability computations, which provide an alternative to that table approach for when you need to update a probability based on additional information. So let's put a bit of a real-world context to this, and let's imagine shoppers over at Kroger or Food City. And let's consider the event A, where they have apples in their shopping cart, and event B, where they have bananas in their shopping cart. So we might be interested in studying how the appearance of these two items is related. Specifically, we might want to know, well, what is the probability that a shopper has apples in their cart given that they have bananas in their cart? Remember that vertical bar is pronounced given, and the event to the right of that vertical bar is the event that we are conditioning on. That's the event that we know has happened, and we want that reflected in our calculation and discussion of the probability of event A happening. So we might know maybe that 1% of all carts over at Kroger contain apples. The prior probability of finding apples is 1%. But the appearance of apples and bananas might be fairly strongly associated. So we might know that if a cart has bananas in it, maybe the posterior probability of finding apples is something like 20%. People tend to buy different types of fruit together. So formulaically, this is the way that we can calculate one of these conditional probabilities. There is a mathematical way to actually come up with these conditional probabilities, and that is to take the probability that both of the events occur, both your event of interest and the event on which you're conditioning, and divide that by the probability of the event on which you're conditioning. Now, there's some terminology. The probability that both the events occur, apples and bananas, happen to be in someone's cart. That's what's known as the joint probability of both of those events. And when we divide by P of B, the probability of finding bananas in there, we can call that as the marginal or unconditional probability of B. Just the probability all by itself, the long-run fraction of carts that have bananas in it, not conditioned on anything else. So where does this formula come from? It's kind of weird to divide two probabilities, with each other. So where does that even arise? How does this make sense? And we can derive this formula visually just with the use of a Venn diagram. So let's imagine that this rectangle here represents the entire sample space of shopping carts. So some have apples, some have bananas, some have both, some have neither. And let's go ahead and color code the region of the sample space that corresponds to event A. In other words, let's color code the rectangle of shopping carts with a pink circle to represent the fraction of carts that have apples. And we'll do the same thing for bananas. This blue oval here represents the fraction of the sample space, the fraction of shopping carts that have bananas. And since sometimes shopping carts are going to have both, we have this bit of a section of overlap here. This fraction of the sample space has both apples and bananas in it. So how can we derive this formula? Well, let's think out loud what this probability is asking us to find. We're asking for the probability that apples are in the cart given that bananas are in the cart. So if I know that bananas are in the cart, I know that my effective sample space isn't this rectangle of all shopping carts out there. Rather, my effective sample space is this blue oval here, because I know that I'm dealing with a cart with a banana in it. And so this is my new sample space. And we talked about that conditional probabilities are just probabilities using a different sample space, a reduced sample space, than what we originally started out with. So the original sample space being all shopping carts, our reduced sample space are just the shopping carts with bananas in them. So we know that we're living somewhere inside this blue oval, the carts with bananas in it. What's the probability that it's also going to have apples? Well, that's going to be where A and B overlap. Essentially, the fraction of the sample space devoted to apples is overlapping with the fraction of the sample space devoted to bananas. And so since the conditional probability is just a normal probability with respect to a different sample space, we can talk about how the probability of having apples, given that bananas are in the cart, is just the fraction of carts with bananas that also contain apples. In other words, I can take the area devoted to A and B and divide that by the area devoted to B. And that's where my formula comes from. If I want to know the probability that A occurs, given that B has occurred, I'm working with a reduced sample space from what I originally started out with to reflect the knowledge that B has occurred. And so that works out to be the ratio of these two probabilities. We know we're living in this blue oval here, the carts with bananas. What fraction of those carts have apples? Well, it's A and B divided by B here. So that's where the formula for conditional probability comes in. And I like just thinking of it in terms of that reduction of the sample space, which I think that table method really brought out. And as long as you just realize that, hey, whenever we're conditioning on new information, we're just reducing the sample space in a way that our brains can't necessarily anticipate, but it's still just, a standard probability, the fraction of that sample space where our event of interest occurs. I think if we think of it that way, then we're going to be good to go. The mathematics just has a bunch of notation that we have to work with. Now, back in Unit 1, we discussed the multiplication rule for what if we want to know the probability that two events occur simultaneously. So, for example, what's the probability that I do not get a parking ticket day 1 and I don't get a parking ticket day 2, two different events? Or what's the probability that a cart's going to have apples and bananas in it? And I threw that formula at you at the time. I said if I want to know the probability of two events, A and B, both occurring, well, that's going to be the probability of A given B times the probability of B, or just kind of swapping the identity of A and B, I can write it this way as well. So where does that formula come from? Where does that multiplication rule come from? Well, it comes from this formula discussing conditional probabilities. If we just multiplied both sides of this equation by the probability of B, well, the probability of B's would cancel out here on the right, and we'd have P of B times P of A given B. And so that's where our multiplication rule came into play. If I wanted to know what's the probability of getting a blackjack in if I'm playing blackjack here, get two cards at random from a deck of cards, well, that's the probability the first card is an ace and the second card is a 10-face card, 10-valued card, a king, queen, jack, or 10. Or vice versa here. So to figure out the probability the first card was an ace and the second card was a 10-valued card, well, that would be the probability of a blackjack one way. We could use that law of, or the multiplication rule to get there. All right, so we can actually rewrite this formula for conditional probabilities in a slightly different way, which we're actually going to find really quite useful coming up, because it turns out that very often the probability of A and B occurring is a little bit too hard to handle. So just taking our multiplication rule and saying, well, another way to write P of A and B is P of B given A times PB, we can recover a much more useful rule for calculating conditional probabilities. In fact, so useful it's given a name. It's called Bayes' theorem. If I want to know what's the probability that a cart has apples, given that there's bananas in them, I can get that by calculating three other probabilities. Number one, the prior probability that apples are going to be there, and then multiply that by a ratio involving probabilities of bananas. Now, this becomes a lot more clear once we start working through some examples, but I wanted to establish where these formulas come from. Bayes' theorem is one of the most important formulas in all of probability, in all of business analytics, and it has this nice mathematical method for updating from prior probabilities to posterior probabilities. Notice if we want to know something about the probability of A occurring and we're throwing in some additional information, we know that event B has occurred, Bayes' theorem gives us a way to do that. We essentially start out with the prior probability, multiply it by something, some number we'll have to compute, to get that posterior probability. So once we know that B has occurred, the probability of A might have gotten bigger, might have gotten smaller. The amount by which it's changing is the ratio of these two quantities here. Okay, so let's do a few basic examples and then dive into it and see how Bayes' theorem works in action for some more real-world problems. So it doesn't get much more basic than this. We're going to pick a random integer between 1 and 100. So it might be even, it might be a square number, the product of its digits might be 36. There's a lot of things we can talk about with numbers here. Let's go ahead and just call event A being the event that the number picked is an even number, 2, 4, 6, 8, 10, etc., etc. Event B is going to be the event where the number picked is a number such that the product of its digits is 36. So in order for that to happen, well, we could pick the number 66, because 6 times 6 is 36. It might be 49, or it might be 94, because the product of the digits there are equal to 36 as well. So 2 events. What can we say about the probabilities of these events? What sort of questions can we answer about the number that we've randomly picked? Well, we could start out pretty basic in asking, what's the probability that event A would occur? What's the probability that I would pick an even number? Well, half of the numbers between 1 and 100 are even, so the probability that I would pick an even number... I'm going to watch to see what I look like when I sneeze after this. So the prior probability that the number picked that was going to be even is 50%. Likewise, we can calculate the prior probability of event B occurring. So what is the probability just in general that the number picked is going to have the product of its digits be 36? Well, there's 100 possible choices we're picking from. Only 3 numbers have the product of their digits be 36. So the probability of event B occurring is 0.03. And in fact, we can answer what's the probability that both of these things occur. What's the probability of getting an even number whose digits, when multiplied together, equal 36? Well, in this case, there's only 2 of these numbers, 66 and 94, so the probability of both occurring is 2%. All right, so let's do some conditioning. Let's say I wanted to know what's the probability that the number picked is an even number given the product of its digits is 36. So I've picked a number. I do know something about that number. The product of the digits is 36. What's the probability now that it's an even number? The prior probability was 50%. What's the posterior probability, factoring in this additional knowledge that I know something about the product of its digits? Well, according to our formula, I just need to take the joint probability, the probability that both these events occur, which we just derived to be 0.02, and divide by the probability of the event on which we're conditioning, the probability of B, the probability that the product of the digits was 36, which we calculated to be 0.03. So 0.02 divided by 0.03, 2/3. So that's a lot of math. That's kind of a lot of work to get into an answer that we actually pretty could have come across without too much difficulty. If we know that the number that was picked had a product of its digits be 36, well, there's only 3 of them. These 3 are equally likely. What's the probability among these 3 numbers of picking an even number? Well, 2 of these 3 are even. So bam, probability that it's even given the product of the digits is 36 has to be 2/3 here. Easy problem, one that we really didn't need math to finish, but it shows you how the formulas play out in action here. Cannon and Jackson, how did you get into my lecture here? Well, I'm glad you visited because I'm going to use you guys as inspiration for the next question. So we actually do have pet insurance on our two dogs. Frenchies are notoriously fragile, especially with their spines, and if they get hurt, the spinal surgery is a lot of money. So it's pretty common for Frenchie owners to actually own pet insurance to help defray some of the cost of getting them fixed up. Luckily, our boys so far haven't had any major issues, so hopefully that'll continue into the future. So let's tie it a little bit back to our work with the table approach and see how these formulas for conditional probabilities work in action with people owning pets and people buying pet insurance. So we're going to dive into, say, PetSmart's customer database, and we're going to look at 100 customers of PetSmart here. All right, so not everyone who shops at PetSmart has a pet. Some people that actually don't have pets might have bought pet insurance, say on the behalf of someone else. And so let's break down the combination of having and not having pets and buying insurance and not buying pet insurance through PetSmart here. So in our data, we have 100 total people. And based on the transactional records, one thing that we know is that 79% of the customers actually do have a pet, and the remaining 21% do not. And likewise, one thing that we know is from those transactional records, those 100 customers, 10 of them have bought pet insurance at some point through PetSmart in the past, whereas 90 have not bought it. So let's answer some probability questions about the event having a pet or not having a pet, buying pet insurance, not buying pet insurance, and then some combination of those two as well. So number one, let's just say A is the event they have bought pet insurance. What's the probability if we pick one of these 100 customers at random that they will have bought pet insurance? Well, there's 10 of them over 100. We're going to get 10% for the prior probability that a customer has purchased pet insurance. What's the prior probability that the randomly selected person is going to have a pet? Well, there's 79 pet owners in our sample space out of the 100, so that prior probability is going to be 79%. What's the probability of both? That this randomly picked customer will have bought pet insurance and also owns a pet? Well, there's 9 that have both these properties in common. Can't quite highlight that. So 9 out of the 100 gives us 9%. Okay, so what about some conditional probabilities here? One thing I might want to know is, well, what's the probability that a customer has a pet given that they have bought pet insurance? So let's actually use the formula approach first. I want to know what's the probability that someone has a pet given that they have bought pet insurance. So from the formula, I need to take the probability that both of these have occurred, that 9%, and divide by the probability of the event on which I'm conditioning, which is 10%. So 9% over 10%, that works out to be 9 out of 10, or 90%. Easy to work with the formula. Easy to look at with this table as well. If I know that someone has bought pet insurance, then I know that we're living somewhere in this column. Our reduced sample space are these 10 customers. Our original sample space was 100, but once we condition on the fact that they've bought pet insurance, we know we're dealing with one of these 10 customers. And if one of them is randomly picked, well, we see that 9 out of those 10 customers have a pet. So the probability works out to be 90%. And so this looks very much like the table approach. So if we knew some of these prior probabilities, having a pet, not having a pet at 79%, 21%, and filled out the table with the stuff that we're conditioning on, the buying pet insurance, not buying pet insurance, we would come out with the same numbers if we had taken the total number of people in our table to be 100 here. So it's a nice convergence of no matter how you look at it, as long as you're working through the math or filling in the table correctly, you'll get to the same answer either way. Now, I want to revisit one of our first a little bit sexist examples about the librarian versus waitress. So quick recap, we were talking to a friend. Our friend shows us a picture of a girl. We think she's cute. And we ask, hey, what does she do for a living? And your friend's like, I don't remember, but she was either a waitress or a librarian. And so there were some questions. I wanted to know, well, which is more likely? knowing nothing else about this woman, is it more likely she's a waitress or more likely she's a librarian? And then I threw some additional information at you. She's quiet, she dresses conservatively, she likes to read, she's very smart, she wears glasses, kind of like your stereotypical librarian description. And I said, conditioned on that information, now, which is more likely? She's a librarian or she's a waitress. So let's use Bayes' theorem here. Let's use our math version of conditional probability to come up with an answer. So I want to know, given this description of her, those 5 adjectives, the intelligent, quiet, dressed conservatively, smart, likes to read, given those 5 adjectives, what's the probability that she's a librarian? Okay. Our law of conditional probability says probability of A given B equals the probability of both divided by the probability of B, the event on which we're conditioning. So we could try to calculate it this way, but getting the probability that a woman kind of randomly picked is both a librarian and matches that description, that's hard to get data on. So that's not something I can just look up easily. And so I want to use that alternative description of how to compute a conditional probability. I want to use Bayes' theorem to calculate this instead. So what is the probability that the woman is a librarian given this 5 adjective description? Well, that's the prior probability she's a librarian times the ratio of these two things. The bottom, the probability just some random woman out there, either a waitress or librarian, would match that description. And then the top would be, given the librarian, what's the probability she meets that description? In other words, how often is this stereotype true here? So some of this stuff we can look up online. So you can go and look to see how people are employed in various professions. And when I looked this up, it seemed to be that there were about 120,000 female librarians and about 1.4 million female waitresses. So with this in mind, if we know that, or if we assume that we're randomly picking one woman from this pool of librarians/waitresses, then we know the prior probability that she's a librarian is pretty small. It's pretty unlikely here. There's 120,000 librarians divided by the total pool of these two numbers added up. That works out to be just under 8%. So just without any other information, asked, hey, is this randomly picked woman here more likely to be a waitress or a librarian? Well, much more likely to be a waitress. So now, how do we factor in the additional information that we have? We want to condition our probability that she's a librarian on this description. We're updating our understanding of reality here. And so one of these probabilities we've calculated, the prior probability, we need the remaining 2. How often is the stereotype correct? Among librarians, what's the probability that she matches that description? And just in general, among waitresses and librarians, how often does that description apply? So we'll need a little bit of guesswork. And for the top probability, basically how often are stereotypes true? What's the probability that a librarian would have that description? I'm going to say that the stereotype is pretty darn true. I'm going to say that 70% of female librarians match this description. You can disagree and redo the calculation with different numbers, but we'll take 0.7 as our number here. All right. Now, the other part, that denominator, was the probability of a randomly picked woman, waitress or librarian here, matching that description, the unconditional probability of being smart, quiet, likes to read, dresses conservatively, and wears glasses. And let's say that that's really not that rare of a combination of traits. Let's imagine that that applies to 15% of women if we pool together all of the waitresses and librarians here. So we can throw these numbers now into Bayes' theorem and get our answer. We have the prior probability of being a librarian, just about 8%, 70%, how often that stereotype is true, divided by that 15% of just a random woman, waitress or librarian having that description. And so getting that posterior probability now that she's a librarian given that description, well, using our numbers, that works out to be only about 37%. So even though this woman that we're discussing kind of meets the stereotype of a librarian to a T, it's still more likely that she is a waitress. And so this is kind of tying back into the medical test example. having that disease was so rare that even when that test comes back positive and the probability increases a lot, you're still more likely to not have that disease. Same sort of thing going on here. Being a librarian is so rare that even when you meet the description of a librarian kind of to a T, that does boost up the probability a lot, but it's still more likely that she's a waitress just because there are so many waitresses out there here. So you could redo this question with your own set of probabilities. You might see the answers go up or down depending, but it's kind of a nice way to use some data to help us out with the computation. All right, so most of the time, anything worth studying in business analytics has some association. Someone who buys product A is either more likely or less likely to buy product B. If we're going to look at probabilities of donating, there are certain types of students that graduated that are more likely to donate on average, others that are less likely. There's some sort of an association between characteristics and donating. And from a business analytics standpoint, that's great news because if everything was just random, our field really wouldn't exist. We'd have nothing to say. The only time when we kind of hope where things aren't really related to one another, that they don't have an association, is when we want to make the math work out a bit easier. We've talked about independent events, events that have no association whatsoever, and we've seen that the multiplication rule for independent events is really quite simple. And in fact, that has strong implications for what our mathematical rule for conditional probability computations work out to be when we're dealing with independent events. Namely, if we have two events A and B that are completely independent, say the probability of 20 or more people going to the Weigels down the street tomorrow and the probability that it's less than 60 degrees in California tomorrow. Those two have nothing to do with each other. They're basically independent. If we have independent events, this is how simple that conditional probability formula works out to be. The probability of A given B is just the prior probability of A, the overall fraction of time A occurs. And it makes sense. If B doesn't really have any sort of bearing whatsoever on whether A does or doesn't occur, well, of course, knowing that B has occurred isn't going to change the probability that A occurs at all. So the posterior probability is the same as the prior probability. If two events are unrelated, knowing one happened doesn't change the probability of the other happening. So both ways of writing it, if we have independent events, the posterior probability is just the same thing as the prior probability here. So some examples of independent events, well, Powerball numbers. Unfortunately, if you go through the entire past history of Powerball numbers, that looks like that the numbers that are drawn from week to week to week are independent. So if you were going to look at event A being 11 is picked in the Powerball this week, and B being the event 11 is picked in the Powerball next week, well, those two events are independent of one another. If 11 is picked this week, that really has no bearing whatsoever on the probability that 11 will be picked next week. Likewise, if you're playing the stock market trying to make a lot of money, event A might be that the closing price of Apple stock is greater than $200. Event B might be the event that the daily high temperature in Knoxville is 92. Two events not really related to one another. You're not going to be able to use the weather in Knoxville to predict the closing price of Apple stock, most likely. Those are independent events. So some things in the world are independent. Most things that we study in business analytics are not independent. They have some sort of association. We know that the probability of the event that someone buys gas next week is going to be highly tied in to whether or not they do or don't own a car. If they don't own a car, they're probably not going to buy gas next week. If they do own a car, chances are pretty good. Likewise, event A being someone wearing shorts, event B is the daily high temperature in Knoxville. Yeah, pretty strong relationship. If the temperature is low, only those die-hard shorts aficionados are going to be wearing shorts. There's always that one person, it's like 30 degrees outside, and they're just trotting around campus in shorts. I'm like, aren't you cold? I guess not. If the temperature is really warm, yeah, probably going to be wearing shorts here. I want to revisit Bayes' theorem and talk about a pretty major complication to using it in practice. So when we wrote out Bayes' theorem, we said, okay, here's a mathematical way to go from the prior probability of some event occurring to the posterior probability of that event occurring, given some new information, given that we know that event B has occurred. Now, the major problem with Bayes' theorem is that we have to divide by the probability of B, divide by the probability of the event on which we're conditioning. And a lot of times, that's going to be a head scratcher. Let me illustrate this with an example. So I play video games way more than I really should. Maybe you do too. And so let's do a video game example here. So let's imagine we're playing, a two-person fighter game. We're playing against the computer here. And the way that the match works is that your opponent that you're going to face next is randomly selected. But there are a few different options. The opponent might either be a hard opponent, an average opponent, or an easy opponent. And you're never privy to what the difficulty level of your opponent's going to be. It's one of these three. And they're not all equally likely. In fact, it's more likely than others for you to be faced with an easy opponent, followed by average, and then hard only at 20% here. Now, obviously, easy opponents are going to be easier to beat, harder opponents harder to beat. Let's say that based on your skill level, the probability of you winning against a hard opponent is only 10%. Whereas the probability of you winning against an easy opponent is 80%. So, opponent randomly selected, they're going to vary in difficulty. Not all difficulties are equally likely. And then you're either going to win or you're going to lose. But those win probabilities change depending on the difficulty of your opponent. So, what happens? Well, you play your next opponent and you win. Good job. So here's my question. What's the probability that that opponent was hard difficulty? In other words, given that you won that match against your next opponent, what's the probability that that opponent was hard? Okay, no problem. That's a Bayes' theorem question. That's conditional probability. Let's write that out in its three component numbers. So first we take the prior probability that the video game opponent would have been hard. No problem at all. That's just 20%. Then what we do is we multiply that by the probability of winning against a hard opponent. So given the opponent's hard, what's the probability you win? That's no problem at all. If the opponent's hard, you have a 10% chance of winning. And now is where we're going to frown a little bit. We need to know the unconditional probability that we would win a game. But that wasn't given to me. And the probability of me winning depends on the opponent type, which is randomly selected. And so we're a little bit stuck here. The probability of winning, the unconditional probability of winning, just the long run fraction of games that we win, isn't immediately apparent by the information that's been presented to us. And so here's going to be a useful trick that we can use in order to get that denominator. It's going to be called partitioning, and that makes sense once we learn what it's doing. How can we try to get this probability of winning here? Okay, well, my favorite thing is to approach the problem visually. That was the theme of the table approach, and let's do something similar here. So what I'm going to do is I'm going to draw a rectangle to represent our sample space. So the sample space is the difficulty level of our opponent next match, and then factoring in some information about whether we win or we lose. So let's split up the sample space into 6 different components. We know that there's a 50% chance of being matched with an easy opponent, so let's go ahead and just shade half of the sample space to be green. And then within that green, let's split it up into win and lose, because we know there's an 80% chance of winning, 20% chance of losing in there. So 80% of the green region is going to be devoted to win. Now, average, we face that opponent 30% of the time. So let's shade 30% of the sample space yellow. And one thing that we know is that if we're faced with an average opponent, there's a 50-50 shot of us winning. So that yellow region will split into 2 equal-sized bits, one lighter yellow, one darker yellow. A hard opponent, well, we only see a hard opponent 20% of the time, so let's shade 20% of the sample space to be red to represent that we're facing a hard opponent. We don't usually win against a hard opponent, 10% chance, so let's shade 10% of that red area to represent winning here. Okay, well, the total area of the rectangle is 100%. We just need to figure out, okay, what's the probability of winning? We essentially need to add up these 3 areas, the dark green, the dark yellow, and the dark red. So all of that corresponds to winning in our sample space here. We just have to figure out, okay, well, how much of the area is devoted to this dark green square, the dark yellow square, and the dark red square. Add those three up, and we'll get the probability of winning. All right, so formulaically, kind of operationally, here's what we're doing. Here's what we just reasoned into. If we want to know the probability of winning against a random opponent here, well, we need to do three things. We need to add up three quantities. The three dark regions where we win against an easy component, win against an average opponent, and win against a hard opponent. In other words, we're taking the probability that the opponent that we face next is easy and we win, plus the probability the opponent is average and we win, the dark yellow, plus the probability that the opponent is hard and we win, this dark red area. So mathematically, when we were just talking about adding up these three areas, that's what we were doing in equation form. Just adding up probability of winning easy to the probability of winning in average to the probability of winning in hard. Now, one thing we know is how to get these percentages. It's really not too difficult to reason through here. Let's tackle the green one first. Let's try to figure out what is the area of the dark green region. All right, well, one thing we know is that the green region fills up 50% of the sample space because there's a 50% chance of us being matched against an easy opponent. Okay, so what fraction is dark green? Win. What fraction is light green? Lose. Well, we knew that we have an 80% chance of winning against an easy opponent, so 80% of this green area must be dark green. All right, well, 80% of 50% of the sample space, 0.8 times 0.5, works out to be 40% of the sample space. So the area of this dark green rectangle right here is 0.4. That's the probability of facing an easy opponent and winning. And we can apply the same logic to these other regions. We know that we have a 30% chance of running into an average opponent. The yellow area represents 30% of the sample space. There's a 50-50 shot of winning versus losing, so I know that the area of the dark yellow region must be 15% of the sample space, half of that 30% devoted to running into an average. All right, and then finally, for the hard opponent here, we know 20% of the sample space is devoted to hard opponents. And we know that we don't usually win, only 10% of the time do we win against a hard opponent. So 10% of this 20%, 0.1 times 0.2, 2% of the sample space here is devoted to dark red. So, all right, we have the percentages. We've split up our sample space into these 6 regions. We've labeled each of these regions by what percentage of the sample space falls into them. We see that win, win, win add up to 40 plus 15 plus 2, or 57%. So what we found is actually we can calculate the probability of winning against our next opponent. It's 57%, but we had to take a bit of a trip to get there. It required us to do a few computations. Now, we just reasoned through that using kind of logic and words. So let's try to operationalize that by writing down an equation that captures what our thought process was. So we said, okay, I want the probability of winning. And we said, okay, that's the sum of 3 different areas. That was the dark red, the probability of winning against a hard opponent, plus the dark yellow, winning against an easy or an average opponent, plus the dark green, winning against an easy component here, or opponent here. And then what we did is we just kind of used logic to figure out what this joint probability was, winning against a hard opponent. And implicitly what we were doing, we were using the multiplication rule. We were saying, okay, well, what's the probability of win and hard? Well, that's the probability of running into a hard opponent times the probability of winning against that hard opponent. 20% chance of getting a hard opponent, 10% chance of winning against that hard opponent. Multiply those two together, that was that 2% of the area of that dark red. So when we were asked to find any one of these 3 components here, what we did is we were using the multiplication rule, whether we knew it or not. If we wanted to know what's the probability that we win against our next opponent and he's easy, well, that was the probability, the fraction of the sample space devoted to the easy opponent, that 50%, times the probability we would win against that easy opponent, that 80%. So 0.5 times 0.8 worked out to be what we had before. So really, mathematically, all we were doing is we were splitting up these joint probabilities, win in hard, win in average, win in easy, using the multiplication rule. We said win in hard is just probability of win given hard times the probability of hard, the probability of running into a hard opponent, and then winning against him, plus the probability of running into an average opponent times the probability of winning against them, etc. And so this is what the partitioning trick is trying to get out of. I think visually the partitioning makes sense because we're taking the sample space and partitioning it into various bits, and we're adding up the appropriate bits to get the probability of our event of interest. And we can also think of partitioning as essentially taking, overlaps of events and splitting them up into probabilities that we can actually compute based on the information that's given to us in the problem itself. So summary of that problem, here's the probabilities of the different opponent types. Here are the probabilities of winning against those opponents. Mathematically, this is what we've discovered or come across for how we calculate just the overall probability of winning, which we reason through to be 50%. We can get it the math way, we can get it just through logic and reason here. And this process where we piece together those different smaller probabilities to get what we wanted, that is what's called partitioning. And so this is the partitioning trick. One of the most powerful things that you can do in probability, because it allows you to calculate really hard things based on piecing together easier to calculate parts. So mathematically, if you love equation speak, this is how you would write it. You essentially identify a set of events that form a partition, like the difficulty of your opponent, and then you piece together the probability of your event of interest here, B, of winning, by considering all possible events in that partition, all different difficulties that you might have run across. Now, sounds a little bit much in just words, and I promise that once you've done it a few times, it's actually not all that bad in practice. You kind of get into a rhythm and you're able to write it down fairly easily. So let's go ahead and run through a few problems so that we can see how this partitioning trick kind of works in practice, and what other better way to do it than revisiting the problems that we originally addressed, the ones that we solved with the table approach, and that we'll resolve now using Bayes' theorem. So back to the rare disease problem. We have that this rare disease affects 0.04% of the population, but the tests are pretty good. If you have the disease, it comes back positive 99.9% of the time. If you don't have the disease, it's going to come back negative 98% of the time. Only a 2% false positive rate. So what happened to us? Well, we went to the doctor, we got tested for this disease. The test came back positive. So on the surface, really bad news, but the question was, given this positive test result, what's really the probability that we have the disease? We know the answer is actually still pretty small from the table approach. Let's see Bayes' theorem in action and how we could get to this number just by using math in the equations. And if you love living in math and equation world, this might be your thing. If you love table world, I love table world, I love math world too actually, I'm pretty flexible, then feel free to stick there. All right, so here's what Bayes' theorem has to say about the probability that we want. We know that our test came back positive. Given that positive test result, what's the probability that we are a carrier of the disease? What's the probability we're infected? Bayes' theorem says, okay, we'll take the prior probability of you being infected and then multiply it by the ratio of two probabilities. The probability that you would actually come back with a positive test result, given that you were infected, divided by just the general probability of the test coming back positive. So if you haven't noticed the pattern yet, here's what I've always noticed. If I want to write out Bayes' theorem, essentially infected given test, what I do is I flip the ordering of these events around the bar. That's the first part of the numerator of the fraction. The prior probability is always going to be there as well, so the prior probability of the event to the left of the bar. And then we divide by the probability of the event on which we're conditioning. So that's how I kind of remember what Bayes' theorem looks like. You can always look it up. And so what do we know? We know the prior probability, that's that 0.04%. So that part's done. We also know the probability the test comes back positive, when we're infected. That's that 99.9% or 0.999. The rub, the difficult part is, well, what is the unconditional probability, just in general, of the test coming back positive? Head scratcher because, well, that depends on if we do or we don't have the disease. So let's do this partitioning and come up with an answer for that. What is the probability, just in general, that the test comes back positive? Well, in this case, our partition is going to be our disease status. That's what influences the results of that test, if it coming back positive or negative here. And so since there's only two options for the disease status, our partition only has two elements in it. We have it or we don't. So let's go ahead and partition in order to get the probability that the test would come back positive. How do we do this? Well, here's my trick for writing it out. What I do is I say, well, I know that the test coming back positive depends on my status, if I do or if I don't have the disease. So I'm going to go through methodically, and for each one of those possibilities, I'm going to write out a conditional probability and multiply it by a prior probability. So the probability of me testing positive, well, one way that can happen is if I do have the disease. So let's write out that conditional probability of testing positive given that I have the disease times the prior probability that I'm infected. So these two are going to be matching up. Whatever you're conditioning on, that's going to be the probability that you multiply to the right of that unconditional probability there. So one way of it testing positive is I'm infected. The other way is that I'm not infected. So we'll add in the probability of testing positive with no infection times the probability of no infection, the prior probability there. Notice once again, these two match up. So when you go and actually write this out in practice, you just think about, okay, well, what are all the events in my partition here? And you're just going to take this event here, slap it to the left of the bar, and for each one of those events in the partition, it's going to be bar one event times the probability of that event going through each event one in turn. And these will always be given to us. What do we know? The probability of testing positive given that we're infected, that's that 99.9%. The probability we're infected, that prior probability, 0.04% here. What's the probability we test positive given that we're not infected? Well, that's that 2%. We know that there's a 98% chance it comes back negative if we don't have it, so there must be a 2% chance it'll come back positive. And the probability we're not infected, well, that's the complement of being infected. That's going to be 0.996, 1 minus 0.0004 here. So plugging in the numbers, doing the math, we find that overall 2.04% of tests are going to come back positive. Okay, so nice to know, cool story. Let's put them all in the relevant parts of that equation and come up with our answer. So Bayes' theorem, we already knew what the top two numbers were in this equation, plugging those back in and then plugging in the probability that a test comes back positive, that 0.0204%. We recover that number that was slightly less than 2%, the same thing that we got back in the table approach here. And so that positive test result didn't really mean much. And the reason why it doesn't mean much is because that disease is just so exceedingly rare. Our prior probability was 0.04%. Sure, it increased by a factor of about 50 up to 2%, but it's still really quite unlikely to have it. All right. Last example, let's revisit the digit recognition problem. We worked through it with the table approach. Let's work through it with Bayes' theorem as well. So what we know is that this machine is scanning all the digits on envelopes, and the machine just said, hey, this digit is a 3. And we want to know, okay, well, is it actually a 3? We want to know, given that the machine is claiming a 3, what is the probability that it actually is a 3? So how would we calculate that with Bayes' theorem? Well, let's do my trick. So to rewrite this, we kind of flip the ordering of the events around the bar. That's going to be our first component up in the numerator. We multiply that by the prior probability of our event of interest, the probability that it's actually a 3. And then we divide by the probability of the event on which we're conditioning. So the event to the right of the bar gets slapped down into the denominator. Two of these three things we already know. We know the prior probability that it's actually a 3 is 10%. One of the things about this problem was that all the digits were equally likely. We also know the probability that the machine's going to claim it's a 3, given that the number actually is a 3. Part of the problem said that this was a pretty good recognizer. It had 91% accuracy, so if it really is a 3, the machine's going to say, hey, it's a 3, 91% of the time. The problem thing is always in that denominator. What is the probability that the machine is just going to claim that it's a 3 on some random digit? Why is that so hard? Well, that depends on some things. It depends on if it is a 3, if it was an 8, or if it was some other digit here. There are different misclassification rates. And so here's where we have to do some partitioning to get that value in the denominator. So how do we do this partitioning? Well, we think, all right, how is claiming a 3, what is that going to depend on? Well, that's going to depend on what the actual digit is. And so we'll use the actual identity of that digit as our partition, those 10 different options, and we'll have to go through and write out that really long partition equation. So we need to know what's the probability that the machine's going to claim a 3. Right? Depends on if it's a 0, or if it's a 1, or if it's a 2, it's a 3, it's a 4, etc., etc. So let's write out all those options. So when we do that partitioning, what do? Well, we simply rewrite probably our event of interest, and then slap a bar right after it, and then go through methodically each one of the events in our partition. We know it depends on if it's actually a 0, so we start out by saying, all right, well, that's the probability it's a 3 given that it's a 0 times the probability it's a 0 plus the probability that it's claiming it's a 3 given it's a 1 times the probability it's a 1 plus the probability that it claims it's a 3 given it's a 2 times the probability it's given a 2. And we go down and exhaustively enumerate all 10 of those events in our partition, the actual identity of that digit. So it's a long equation. That's why we got those dot, dot, dots there. I'm not going to write that whole thing out. But at the end of the day, we can go through, plug everything in there, plug it back into Bayes' theorem, and we end up with that 91.55%, the same value that we got in the table approach. So there we go. If we have to calculate a conditional probability, first thing is that we should stop and we should say, hey, brain's not so great at doing that automatically. We're not so great at updating from prior probabilities to posterior probabilities. We need to be careful. So recommendation number 1, do the table method. I think that shows a really clear way of how the sample space is changing when we're conditioning on more and more and more events. If you want to do the math approach in Bayes' theorem, the partitioning trick, have at it. You're literally doing actually the partitioning in Bayes' theorem when you're doing the table approach. You're just not being intimidated by the scary equations and the scary words. So that's why I like the table approach, because you're doing the whole thing. You're just feeling good about it. So table approach or the Bayes' theorem approach will get to the same answer either way. And so you can stop and you can say, I did not expect that. And almost all the time, you'll be like, I did not expect that number. Conditional probabilities just don't jive very well with our intuition. And so I actually have a theory about why we're terrible at conditional probability. It's not really my own theory. I've read some stuff. It kind of takes from what other people have said as well. But here's what I think fundamentally is going wrong in our brains and why we don't really get how to update from prior to posterior probabilities correctly. So here's what I think is going on. So we're interested in knowing the probability that A occurs once we're given new information. So I want to know, what's the probability that I have this rare disease given that this test has come back positive for the disease? So I need to calculate the probability of A given B, positive given that test result. But here's where I think our brain messes us up. We want the probability of A given B, but we intuitively look at the reverse. We flip the conditional, we get that number, and we just instinctually feel like that's correct. So 2 examples. We wanted the probability that we had the disease given that we tested positive. What did your brain latch onto? Well, your brain latched onto the number of, all right, if you have the disease, what's the probability of you testing positive? Basically, these 2 events flipped around the bar, the probability of testing positive given the disease. That's that 99.9%. And your intuition said, uh-oh, that positive test result, almost in your certainty that I have that disease, because that test is so accurate. Likewise, same thing for the librarian example. We were being asked, all right, well, what's the probability that she is a librarian given that she met the stereotype And what our brain kind of instinctually did is it said, well, let's think about the probability that she would meet the stereotype given the librarian, that 70%, whatever number we had it. And we just kind of felt like that was the answer. Depending on how true that stereotype was, whatever that prevalence of that stereotype was, we just kind of felt like that was the probability. So there's a cognitive bias called flipping the conditional, and you might be able to Wikipedia that. But I think that's what's really going on. Our brains just kind of instinctually flip the ordering of the events around that bar. We can get that number out, and we just feel like that's the right answer. And we need to do it the other way around.